Okay, so today we're going to start our third installment of ELE 475 computer architecture, and this is going to be more review, and we're going to finish up talking about hazards, and today we're going to be talking about control hazards, and then a little bit later we're going to start talking about caches and why we have caches. So let's start off by looking at control hazards, and just to recap, the four different types of, the three different types of hazards we've talked about in this class so far. We were talking about structural hazards, data hazards, and now we're going to talk about control hazards. Okay, so what exact information do we need to calculate the next program counter? Well, is it the same thing for every instruction? When we go to execute an arithmetic logic instruction, an add instruction, do we need the same information to calculate the next program counter? You might say, well, isn't there some piece of magical hardware which just calculates the next program counter? Well, yes, but we need to talk about what that magical piece of hardware is. So as you might guess, it's actually different for branches and jumps than it is for sort of more traditional instructions or arithmetic logic instructions or everything else. So let's start off by looking at jumps. So if we look at a jump, you need to look at the opcode to make sure that it's actually a jump. You also need to look at the offset within the instruction. And you need to look at the current program counter. And you take that all together, and you're like, oh, it's a jump. The decoder says it's a jump. The decode pipe stage of your processor says, OK, it's a jump. And then you can take the program counter, add it to the offset, and you probably need to do that either in the ALU or if you need a special adder to do it. And the pipelines we've drawn so far on our 5-stage pipe, we had a special adder just for that. And you do that offset calculation, and then you want to go and vector your machine so that the next instruction you go to execute is at the target of the jump. Now, this gets a little more complicated when you start to look at jump register. So jump register, you don't know where you're going until you go decode the instruction, fetch the information from the register file. Conveniently, at least you don't need to do some conditional calculation, but you will down here. But we're just going to have to look at the opcode to know that it's a jump register. We don't need to look at any offset because we are jumping directly to a register value in something like MIPS. In other instruction sets, you might need to look at other sorts of information. So you might have, for instance, a register indirect jump register type of instruction, or even a memory indirect jump sort of instruction. Conditional branches, now things start to get a little more complicated. We need to look at the opcode. We need to look at the current program counter. We need to go look at the register, which is going to give us the condition. So we're branching based on whether some value is, let's say, greater than or less than 0. OK, so we need to go look at that, but we don't really know that until quite a bit farther down the pipe. And we also need to take the offset and add it to the program counter when we do a PC relative conditional branch. That's how it's defined in MIPS. In other instruction sets, you can have different types of conditional branches, either a absolute addressing scheme or something where it might be register, indirect, or some other thing like that. But for MIPS, we're just going to take program counter, add it to our offset, and branch that if the register is the register or the condition is what we're looking for. If not, you want to just fall through and go to PC plus 4 or the next instruction if your instruction is 4 bytes long. OK, everything else. Believe it or not, we do need to actually think about this case. It's not some magical piece of hardware. We're going to discuss this magical piece of hardware today. You need to take the opcode, and you need to take the PC, and you need to add some constant to it to compute that you want to fall through to the next instruction. So when we're looking at this, we might have to look at the program counter, but we also have to look at information which comes at different stages in the pipeline. The opcode doesn't get decoded probably until something like the decode stage. Registers don't get fetched, let's say, until the instruction register fetch or decode stage. And For condition, you may even need to do some comparison of 0 or comparison with another register. So you need to do some math or run it through your ALU in your execution stage. Something like jump register is similar there. You're not going to know the destination until maybe once you've gotten to the either execute stage or possibly way, way at the end of the decode stage. So let's take a look at a basic control hazard. And the basic control hazard is we want to execute an instruction, and we want to fall through to the next instruction, which sounds pretty basic, but you would say, why is there any structural hazard there? We're not changing the control flow. So let's draw the pipeline diagram. Assuming that we have no branch delay slots in our architecture, we'll talk more about branch delay slots in a second. Let's draw a pipeline diagram here. So we're going to plot time, and then we're going to step through a basic instruction sequence here. And this basic instruction sequence, actually let's start here. We're going to have instruction 1 and instruction 2. Instruction 1 is taking some register and adding it to something else. We talked about there being data dependencies or data hazards. In this case, there is no data dependence and no data hazard here. You'll see that this is writing to register R1, and this is reading from register R2. So there's no data hazards here. We just want to look at the control hazard. The first instruction just goes down the pipe, fetch, decode, execute, memory, write back on our 5-stage MIPS pipe. The second instruction starts going down the pipe, and it first goes into the fetch stage. But the problem here is we actually need to stall the fetch stage, or we need to, because we don't know that the second instruction is the second instruction yet. For instance, we don't know that this first instruction is not a branch or a jump. So we don't know the address of the next instruction. That's kind of odd. Now, why do we not know this? So going back to this example here, one thing that's common through all of these different cases is that they all need to decode the opcode. Well, where do we do the decoding of the opcode? Well, we don't do that until the decode stage of the pipe. So we don't do that until here. And we're not able to use that information until the end of this cycle, which would be sort of here. And we would need that information to determine what's going on here. So if we had a branch, for instance, here, where it's not able to get around and change the program counter and change what is being indexed into the instruction memory on this cycle. So what we're going to have to do is we're going to have to insert a decode bubble here for this structural hazard. Now, if we sort of play this forward for more instructions, what you're going to realize is this is not very efficient. Every instruction that goes down the pipe is going to hit a control hazard. And every instruction that goes down the pipe, you're basically going to hit this decoding hazard. And every instruction now takes 2 cycles. So your clock per instruction for this is not going to be very good. Let's analyze that now. So we can draw this in the other pipeline diagram axes and see that what's happening here is let's take the execute stage. We're executing instruction I1, then we're no-opping instruction I2, no-op, I3, no-op, and you compute this all out, you end up with a CPI of 2. So your machine is running at strictly half the performance that you want it to run at. Well, that's not very good. So let's start to talk about some techniques to mitigate the effect of control hazards. And we're going to actually have a whole lecture later in the course about branch prediction, which is one of the main techniques in order to mitigate control hazards. But let's move forward here and take a look at one of these techniques. And this technique is speculation. So what's the solution to this? So the most basic solution is we actually speculate that the next address is going to not be a branch. Or the current instruction is not going to be a branch. The next address is going to be the PC plus 4. So what does this look like in a pipe? Well, there's this nice adder here. We're going to take the PC, and if nothing else is happening sort of later down in the pipe, we're just going to be selecting PC plus 4 on this control path here. So we're just going to be sort of walking down here. We're going to be executing 96, 100, 104, and we're not actually going to even look at the instruction until, let's say, something else more interesting happens. So we can just speculate that the next address is PC plus 4. So that's great, but that adds some wriggles. What happens when we have like a jump here? So this jump, if we speculated PC plus 4, we went and fetched instruction 3 here, which is at address 104, but the jumps says we're supposed to go to 304. So this instruction is not even supposed to execute. So we need some mechanism to kill instructions in the pipeline, kill live instructions in the pipe. So how do we go about doing this? So let's look at a brief example here. So we need some way to kill an instruction. And what we're going to do is we're going to add a multiplexer here, which will multiplex in a no-op. And if we have a jump that gets to the decode stage of the pipe, we're going to wire back in and say, oh, that instruction that we just executed, or that instruction we just fetched, this one here, it's not actually supposed to go down the pipe. We should kill it. So we're going to swing this mux, and right at the end of the cycle, we're going to say, no, it's actually a no-op. We're going to insert into the pipe, and we're going to redirect this multiplexer here to the actual jump location. And this is what I was talking about before about the extra adder here. Here's our extra adder, which is computing our destination. And sometimes people try to sort of put these two things together, but we're going to take part of the instruction, and we're going to take the current PC and add to that, and that's going to compute our new destination of the jump. Yeah, sorry. So here's the control on this mux. We just have to look to see if it's a jump or jump and link, and then we insert a no-op. Otherwise, we actually take the thing coming out of the instruction memory. So let's look at this sort of as things flowing down the pipe. If we have instruction 1, the add at the beginning of the execute stage, instruction 2 here now in the decode stage, and we just fetched 104 out of the PC. As we go forward one cycle, we're going to actually take what we took out of the instruction memory that was 104, and we're going to kill it and put a no-op in its place. The jump is now entering the execute stage. The add is entering the memory stage. And we've redirected the front of the pipe here, and we're actually fetching now the destination of the jump, or the instruction at 304. So important question pops up here on the screen. What happens if we have a stall and a jump in the decode stage at the same time? Are there interactions here that we should be worrying about? That's a tricky one. Well, the first question is, what is a jump? What are reasons that a jump would actually stall in the decode stage? It's not a whole lot. In a basic pipe, probably a jump would not actually stall in the decode stage. In more complex pipes, there are sometimes just stall signals that say there's some big structural conflict later in the pipe. Just stall the whole rest of the pipe. So it is possible for things to stall. One important thing is that in a very simple pipe like this, if you have a stall, let's say there actually is some reason this jump is stalling, and you have a jump in that stage, what happens? Sort of, do we kill the instruction? Do we let it go forward? Both of them are actually possible to do. More complex pipes might even think about actually allowing the jump to happen and sort of squishing out any no-ops that get inserted later on in the pipe. And let's look at that from a pipeline diagram perspective, because that might shed a little light on this. And instead of drawing this instruction as continuing down the pipe, we're just going to put no-ops here, or dashes, there. So the first instruction goes on the pipe. The jump goes on the pipe, doesn't stall on anything. Because we have the PC+4 speculation, there's no stall here. This add gets fetched, but doesn't ever make it into the next stage of the pipe because it gets killed. Then we have the next add, or the target of the jump, showing up, and we go and execute that. And if we look for the resource utilization, we can plot it the other direction. You'll see the no-op moving forward in pipe stages over time.